Now again, I've got my mic plugged in here, so don't let me walk too far away. Where am I?
Oh, we were on the last.
Yeah, we were going down here.
We were trying to guess.
Right here. This one.
Yes, this one.
What's this one? Wait, no, did we?
We did this one.
Did we do? We didn't do this one.
No, we didn't.
We didn't do. This is where we. And then I was saying like this one's really cool too. All right, this one.
Oh.
Have a look at this one. Take a moment, look at it, think about it. It's hard to like come up with like. This one I think is easier to analyze if you kind of take a step back and just think about what's going on.
Oh, yes.
If you haven't noticed by now, you could basically ignore these things, right? The first time, like, okay, look, this outside loop is going to run n times. We know that, right? So, like, okay, n. The first time, how many times does this loop, inside loop, run? N. The next time through the loop, how many times does that loop run? N minus 1. Right? No, it's not. No, it's not, because it's additive. The total, it's not we're not multiplying this every time. Your head's in the right place, and not like, oh, okay, n minus 1, n minus 2. Your head's in the right place, but we're not multiplying these things. It's just the total amount of work is how much work is here. N plus n minus 1 plus n minus 2. Or let me flip it. 1 plus 2 plus 3 plus n minus 2 plus n minus 1 plus n. Does that look familiar? Remember we did this a little bit before last semester? First of all, you can think about this. There's a couple of ways we can think about this, right? We can think about this like geometrically, right? What do I have here? It's called a square. All right? But of course, we don't have a full square. We've got like half of the square, right? So it's like half of n squared. But, you know, that's just like that coefficient. We don't care. It still scales like a square. So we can think about it like geometrically like that. But of course, we can think about it like what it is. A series, right? One plus 2 plus n minus 1 plus n, right? And if you remember, this is that whole, okay, 1/2 n plus 1 times n thing, right? And if you multiply all this out, we get 1/2 n squared plus n. It's that n squared thing. So even though it's like, but we're not really doing a full n squared, yes, but it still scales like n squared at the end of the day. Now what about this one? Any questions about what we just did there?
Wouldn't we multiply that by n for the outside loop?
Well, the first time that, like this was one iteration of the outside loop.
Okay.
Remember, the first time the outside loop ran, it went n times, plus n minus 1 times, plus, and so on, right? Good question, though. You had a question?
Yeah, for the Tn, is that gonna be the final answer?
No,
it's like
there'd be
plus?
more. That wouldn't be the T event. There'd be a little bit more to it because we'd be the T event. Let's not worry about it. It doesn't at this point. As we're starting to see, it doesn't really matter so much. We would have to include like okay the constant time stuff. Now this one, what's going on? I'll give you a big hint. How many times is the loop gonna run relative to n? Okay? Don't think so much about how I is scaling, which definitely think of how I is scaling, but keep in mind that n is fixed, right? And so like that loop is gonna run some number of times. How many times is that loop gonna run? Any ideas?
Log n.
Log base 2 of n. It's exactly it. Sure, like, but why? Think about it like this, right? First of all, you'll be like, well, isn't it exponential? Well, the growth of I is exponential. Okay, so the first time, it's like 1 to 2 to 4 to 8 to 16 to 32, 64, and so on. That's growing exponentially, but we are growing exponentially towards like an end. And you can think of it like in reverse by basically being like, well, actually we're halving like every time, right? Think of it like this. Let's say I had 64, n was 64. Don't ask me why, it's just a number I picked. How many times will this loop run? Well, if it was n, this loop would run 64 times, but it's not going to run 64 times. It's going to run 1, 2, 3, 4, 5, 6, 7 times. Maybe 6 because depending on the edge case, right? So this one, I is growing rapidly, which means it is getting towards the end of that loop rapidly. Okay? So yeah, that's a logarithmic one. Log base 2. Any questions about that one?
An easier way to think about it?
Is there an easier way to think about it? I don't know. What do you mean?
Like come to that conclusion?
How quickly do we get to, okay, look, if it's 1, we get 1. If it's 2, we get 2. If we get 3, we get 4. We have
If it's 1, we get 0.
because it's less than?
Yeah.
Yeah, let's not worry. You're right, but let's just think about the growth of these things right now. For 5, we have 16, right? So every time, if we're iterating by 1 every time, we are taking 1 of so many steps towards the completion of that loop, okay? We're taking 1 thing away from the total number of steps remaining. I'm taking 1 more step away, right? If the loop is set to stop running at 64, for example, if I'm counting by 1, every time I take a step, I remove 1 thing. I remove 1 thing. Now here, it starts like that, but maybe it helps if we kind of think about it in reverse, right? So after 16, we have 32 and then 64. So let's say we're at 64. What step would have come, like what would I have been the iteration of this loop before it was 64? 32, which was half of the remaining steps. And then what would I have been before it was 32? 16, which was half of the remaining steps. And then before that, 8. And before that, 4. So in this case, the easiest way to convince yourself is just kind of like draw it out, I think. Yeah. This is not one I want that I expect anyone to be like, yep, makes perfect sense, right? This is something that spend a little bit of time thinking about. But I don't want to get too hung up on this one right now. Any other questions about this though? All right, so now that we've talked a little bit about analyzing these algorithms, okay, here. I just want to check, did I? At this point, there's a bit of a trick that you may have been able to notice. When you want to get the idea of the big O of your algorithms, so far at least, look to the loops. All right, just look at the loops, okay? You've got a loop, okay, it's n. If you've got nested loops, well, paying attention to how they're iterating, but maybe it's like n squared. That's where your head starts to go. So that's kind of like the quick and dirty, easy way to start to get a sense of what's going on there, is look at the loops. Now, really, soon, it's not so much about the loops, it's about like, how many times is this chunk of code going to run? I mean, that's what a loop is, but it's a little bit more general. We'll see shortly. All right, so we have 2 implementations of a stack. We have an array stack and a link stack. But which one's better? Right? Well, let's look at popping and peaking. Here's the link stack pop. What's the computational complexity of the pop and the peak for the array stack? No, link stack. This is the link stack. I'll give you that hint again. Look for the loops. Are there any loops? It's constant time. There could be 1 billion things in this stack, or 3 takes the same amount of time for these pop and peak, right? Oh, so this is a constant time method. That's good. We like that. How about the array stack? Well, again, looks like constant time to me. There's no loops, How much time does it? Well, you just go to the end and check it. Yeah, there we go. That's it. Constant time. It doesn't depend. The amount of time this takes does not depend on how big the stack is. Well, let's think of pushing. Here's the link stack. No loops again. Just create a new node, put the thing in it, set the next, increase size, return true. It's constant. The amount of time this takes does not depend on how many things are in the stack for the linked implementation. But if we look at the array stack, there's a bit of a difference here, right? Like, ignoring this, it's like constant time. But if we have to expand capacity, this is linear, right? First of all, that quick and dirty, I see a loop, right? And the amount of time this is going to take, well, I have to copy everything from one array to another array. How long is that going to take? Well, it depends on how big that array is. If it's twice as big, it's going to take twice as long, and so on. So it's linear. So if you were given a choice between the link stack and the array stack, which one's better? Which one should you use? The array stack? Correct. Now, if you're left going like, wait, what? It's so purely on an algorithmic analysis perspective, from the theoretical total amount of computation, the link stack is the right choice, right? Everything was a constant time operation. Now, the array stack, you go like, well, why is it not so good? Well, because it can be a linear time operation, although I'll briefly talk about something called amortization very shortly. So this one might have a linear time operation, which is, of course, worse, right? It's not happening all the time, but, it can happen, right? Like if I have a stack where the initial capacity is 100, I can do 100 constant time pushes before I have to do one 100-step copy thing, right? Yeah.
Does creating an array depend on the size of the array?
The amount of time it takes to create the array? Maybe? I don't know. I'm going to assume it's constant time to set it aside, but maybe I don't really know. But I don't imagine it is. It's the copying that really is what we're worried about. Now, when it comes to how our computer systems are built, arrays are just like intrinsically faster and easier for the computers to work with. Where moving around memory locations, jumping around because of the link structure is actually slow for the computer. And all of this like creating and setting aside RAM to make a node, putting this in there, deleting that, all that. There's a lot of overhead involved that actually does slow it down. So in practice, the array implementation is, in spite of the analysis, probably a better choice. But that is a consequence of how our computational systems work. That is not a fundamental fact of the universe based on the mathematical definitions of computation and everything. No, not at all. But it is what it is. Now, very briefly, it turns out that this particular thing here that we're saying, like, well, we always think about worst case scenario when doing computational complexity. Okay, it's linear, right? Because it has this. Turns out, if you think about it, I think I have a little link here. We actually kind of say, like, well, who here knows what the word like amortization means? Raise your hand if you've ever heard it before. You've heard it, but what does it mean? It's kind of like saying, like, we can spread out the cost of something over a period of time, okay? Loosely, all right? So what we say is, like, look, I can do, effectively, like, there's a much more detailed description here that you could read through. But I can do n order 1 pushes. I can do n constant time pushes, okay? Constant time, constant time, constant time, constant time. But on that nth push, right? I guess that's n plus 1 because of the 0. But eventually, I have to do a linear amount of work, right? I have to do another thing for each thing that came before it to copy it over, right? But I did do like n for free, n constant time ones. So I can take that like linear time amount of work and like say like, well, if we think that like, if we amortize all of that work that we had to do that one time, and we pretend, well, we did it, like we spread that out over every other constant time operation, it really is just, okay, 2 constant time operations, which is a constant time operation. So there's a little bit of nuance to how we analyze these things like that. Now, for our needs, yeah, it definitely is linear in that, like, okay, we have to do that expanding capacity, but expanding capacity only gets called 1 for every, like, n things. So if we got n, okay, like, free, well, okay, 1, 1, 1, 1, 1, 1, 1, 1, 1, I do that n times. And then I have to do n things, just let's pretend we did 2. Does that make sense? Like if I had n times 1 that way, right? And then I had that n, let's get rid of that 64 so it doesn't throw it off. We have to do an additional n things on that additional thing. Well, I mean, that's still the total of like 2n amounts of work, right? But, let's just pretend we had like n, like n times 2. And you're like, well, yeah, but there's still an n there. Yes, but like each time we called it was only like 1. So if we had like n calls to this that took 2 steps instead of 1, it's all this like mental gymnastics that we do to be like, look, it's linear, but it's not. It's amortized, still constant time. That's all. Neat? I think it's kind of neat. It just goes to show the nuance involved with how we can think about these things. At the end of the day, here's what I want you to take away is, yes, it's linear, but it's not always linear, right? And because of that, we get fancy with our analysis. Any questions about that? Yeah.
It's like an implementation thing, like how you want the processes to do to.
I'm not quite sure what you mean.
Like, I think about it.
Okay. You want to try again? Not yet? All right, let me know. Let me know. All right. All right, a queue. We talked about stacks. Let's talk about queues. Now, we already talked about queues in that we, discussed their idea. But queues are a collection of elements where things are added to one end, but removed from the other. A stack, adding and removing happen from one end, and only one end. The other end was left alone, was the bottom. But a queue, you enter at one and you leave at the other. Stack, you enter and add at the same end. So a queue is like a FIFO, first in, first out. The first thing there is the first thing out. Just like going to line at Starbucks today, right? Like first come, first serve. All right, so if anyone wants to come to the queue, where do they go? Well, if they're following the rules, they go to the back of the queue. And then whoever's served next, well, they leave from the front of the queue. Again, assuming everyone's following the rules. That's it. That's all. It's a queue, right? We all know what a queue is, a line, right? First come, first serve situation. These come up a lot in everyday life and in our computers for programs that we're writing. Obviously, there's a nice way to keep track of first come, first serve situations. So that's a queue. And like other collections, specifically, let's look back to the stack. We want a way to add something to a stack, remove something from a stack, check if a stack is empty. Maybe remember how we had peek? Wait, I'm saying stack. We had a way to add and remove things from a stack. We're going to want that for a queue. We had peek, which was look at the thing, but leave it there. Don't actually remove it. And we had a way to check, hey, is it empty? What's its size? And then we had toStrings and equals because they're always kind of good to have too. So we're going to want the same thing for our queue. So there's a special word we use to mean adding something to a collection when we're talking about a queue, and it's enqueue. E-N-Q-U-E-U-E. This is how we add an element to a queue. The word for add for a queue is called enqueue. Why? Because someone said that. Enqueue, add an element to the collection. The element added will now be at the rear of the queue. It'll be the new rear based on whatever it was. And then dequeue is remove an element from the collection. The removed element will be from the front of the queue, which is not the rear. And the element after the removed element will now be the new front. Okay? So if I'm in line and you're standing behind me and I leave, you're now at the front. Assuming I was at the front. And then the element removed is returned. First, return the element at the front, but leave it alone. Just calling first does not alter the queue in the same way that peek didn't either. And again, like we did with the stack, because everyone always says this, but not you. You guys are better this year. Everyone always says this, but what if I really wanted to access something that's not from the front of the queue? Then don't use a queue. It's not a queue. Our definition of a queue is this. And if you're like, yeah, but then it's not a queue. Simple as that, okay? Use a list or something else. So a queue. Now, if you were to go and look, so Java has a queue built into it. You can go and import a queue. Don't do this, because the whole point of this course is we're implementing this stuff, all right? But if you go and you actually look at Java's queue interface, you're going to see different method names, like enqueue, dequeue are called add, remove. An element is like first, right? And they also have a different set, which is called offer, pull, and peek. The first three are the same as the defined enqueue, dequeue, and first. The other three are the same, but don't throw exceptions. They would throw a sentinel value instead, okay? So that's common. Now you might be saying, why are you using enqueue, dequeue, and first? Well, because that, if you look at the mathematical definition of a queue, if you go to the Wikipedia page for a queue, that's the words you're going to see, right? Java was the weird one. So why they did it, I don't know.
Are most programming languages equally weird, or
Oh, they all have their own weirdness. Why? And you always.
For queues specifically.
Oh, for Q's? No, I don't know. I'm pretty sure, like, yeah, I don't know specifically. I really don't. Yeah. But yeah, if you go look at the Q ADT Wikipedia page, you're gonna find InQ, DQ, and first. So add, remove, and element are like InQ, DQ, and first. If you try to like DQ an empty stack, it's gonna throw an exception. That's what we're gonna do. Here, with their implementation, it's the same idea, but if it's empty, it returns a sentinel value. Maybe null, whatever it says it is. Let's go look. Return special, look at that, return special value. What's the special value? Null, if it's empty. There you go, right? Pull, offer, add, offer, peek, pull, remove. Yeah, anyways. Cool. So example use. Well, really, where would you use a queue? Anywhere where you have a first come, first served thing, right? Like if you're simulating a grocery store, all right, there you go. Cars at a stoplight. An input buffer, right? An input buffer would be something like a keyboard buffer on your computer. You start pressing a bunch of keys in your computer, they get added to a buffer, which basically is like, okay, first come, first served, which key was pressed in which order, right? And then your computer processes it. I mean, it happens really fast, but at the end of the day, there's still an order to the thing of the keys that were pressed on your computer, and your computer goes, okay, what was the order? There's a lot of reasons you'd want a queue. So here's an example. I'm going to warn you, this is a bit of a contrived example, but it totally works. Who here remembers when you were little doing a Caesar cipher? A couple of people? Yeah, you know, that's like where you're like, oh, I'm going to encode a message. I'm going to encrypt it so no one can read it, right? That was the idea of like, okay, so you take some like offset, and you'd say like, okay, I'm going to do an offset of 5 or something, and you take every letter in your sentence that you want to encode, and you like add 5 to it. So if you had an A, you would put an F in what you're writing, right? Why? Well, because A, 1, 2, 3, 4, 5 becomes F, right? Then, if someone saw your message, it would just be a bunch of nonsense. They'd be like, what is this? This makes no sense, right? But if the other person that you wanted to give the message to knew what your K was, all they have to do is go, okay, 1, 2, 3, 4, 5. Oh, it's an A, right? That's the idea. It's a little game that you play as a kid, right? The story goes, Caesar and his generals. I don't know how true it is. Maybe it was, but anyways, there you go. And what's neat here is like it loops back around. Like if you're at Z, it would become, okay, Z, A, B, C. Like it goes back around, because why not? Cool. Now, unfortunately, if you've got a super secret message and you want to encode it because there's a lot of bad actors that want to intercept your message and figure out what you're trying to say, it's actually pretty easy for them to break your cipher. If they know that you've got a Caesar cipher going on, all they have to do is try every possible K value and they'll decode your message, right? What I mean is, okay, here's the message. What if we add 1 to everything? Can I read it? No? Okay, add 2. Can I read it? No? Add 3. Can I read? And so on, right? So, I mean, at worst, how many different letters, how many different offsets do they have to try? 26. Really, only 25 because it's already at the 1, right? So, yeah, at the end of the day, okay, they have to try 25 things. So if I have some string of length n, right? And I need to apply this offset calculation to it for K between 0 to 12, okay, let's say 1 to 25. How much work is it? I mean, it's a constant. Like there's no, like the amount of work, we're not adding any more letters, right? The amount of work I have to do to try to decode it is linear based on the length of the string, right? I have to do it maybe 25 times, but if the string got longer, that doesn't affect how, like the K, yeah.
You probably don't need the whole string anyway.
Exactly, right? Really, you just need a little bit to be like, can I read this?
Yeah,
Exactly,
seconds,
right?
maybe.
You could check a sentence, doesn't make sense, yeah. So really, the point is, it's not that hard. But what you could do is a rotating cipher. A cipher where you say, okay, It requires a little bit more coordination beforehand. You tell your generals, okay, what we're going to do is we're going to use a cipher. And it's not every letter is going to be offset 5. What I'm going to do is I'll say offset 3, and then the next letter you offset 1, and then 7, and then 4, and then 2, and then 5, and just repeat that pattern for every letter. Right? That's what we're going to do. Now it's way harder to break. Still breakable, but a lot harder. Right? Because you have to suddenly try every possible, and you don't know how long, like how many different offsets there are in the rotating cipher. A lot of funny things going on. So suddenly we got a much more sophisticated encoding that's a lot harder to break. Cool? I think that's pretty cool.
And you also actually have 26 options now, because an offset of 0 would still do something.
Absolutely, because you don't really know. Absolutely. So the idea here would be, okay, yeah, so if this is my rotating cipher, I have 3, 1, 7, 4, 2, 5. It's entirely arbitrary, picked out of thin air, it doesn't really matter. But there we go. So first, we take the first letter and shift it by 3, then the next one by 1, the third by 7, the fourth by 4, fifth by 2, sixth by 5. But then, we're out. Well, we just repeat the process. Simple as that. That's all. That's all we do. All right? Neat. So how can we encode this? Well, so first of all, here's the idea, right? If I have like some encoded message and I want to decode it, well, I could just, okay, 3, 1, 7, 4, 2, 5. 3, 1, 7, 4, 2, 5, and so on and so on and so on. So how can we implement this? Well, it's actually fairly easy. What I do is I'll put my rotating key values in a queue. All right? And I've got my string. I start at the first character of the string. Right? What I do is I say, okay, Q, holding my key, DQ. Apply the value, and then I in-queue it back to the back of the lines. So that's what's going on. 3's at the front, then 1's at the front, then 7, then 4, then 2, then 5. But every time we use it, it got re-added. Right? So it's like you got a bunch of people in line. Right? We take somebody out, then they immediately after their process, we just put them right back to the back. That's the idea. And suddenly, great, easy, simple, great, awesome use of a queue. There's a lot of other good uses of a queue, don't get me wrong, and this was perhaps a little bit of a silly example, but a good example nevertheless. Pretty neat. All right, the interface. Don't get too hung up on that example problem, right? You're smiling because it was so good, though, right? Yeah, I know, yeah. So what does the interface look like for our queue? All right, well, we want to in queue. It'll return a Boolean. It takes an element to add. If it was successful, returns true. If it failed, return false. Ours won't ever return false. DQ returns the element. First returns the element. Is empty returns a Boolean. And size returns the size. That's it. That's all we need for a stack interface. So we'll define the interface as public interface queue. It's generic. And that's that. I've ignored the Java comments in this because just for brevity. Otherwise, there's like a million lines of comments for each signature. But that's it. There we go. So just like the stack, when we go and implement a queue, we're going to implement this interface. You had a question?
Would the interface need to have the add remove element in Java? Since it's like 96.
We don't, if we were to go, we are writing our own now. So we just need what we need. Now, if you go and you, like here, let me,
What's the built-in?
so the one that if you like imported queue, Java would be like, here's the interface for a queue, and it includes all of these extra things that we don't want. So that's why we're writing our own. Any other questions or anything? For our needs, just pretend Java doesn't have a queue built in, and we're building it for Java. All right, so let's make a queue. And this time, let's start with a linked implementation. We started with an array implementation for a stack. Let's start with a linked implementation for the queue. So given the definition of a queue, and knowing that I want to use a link structure, how can I actually implement this? Remember, the interface tells us what, and the implementation tells us how. So we know what we want to do. How do we do it with the link structure? So things that we need for the implementation: a container, the link structure. We need a way to keep track of the head front of the queue. Just use a reference to a node. A way to keep track of the rear. Keep a reference to the node at the rear. And a way to keep track of the size, just an integer field. Right? Every time you add something to it, increment it. Every time you remove, you decrease it. There's going to be bookkeeping involved to update all these things, right? But let's also make sure we consider a little bit about the cases of things. When I create a new linked queue, if I have like a head and a tail, okay, front, rear, whatever I want to call it, F and R, these are going to be references to nodes. When I have an empty queue, what should those reference?
Null.
Makes sense, right? Null. I'll just draw null as a dot. Cool, great. Now let's say we have one thing in the queue, right? So we've got some node and its next is null. But notice that, well, when there's one thing in the queue, the front and the rear are the same thing. So we got to be a little bit careful with that. And finally, the other case is going to be like, well, the more general case. Where rear is like that. Now, if I want a DQ, well, that's just removing from the end, or from the front. We know how to do that. If we want to InQ, well, that's just adding to the end. Okay, yeah. All right, so there we got some ideas down. So let's actually start sinking our teeth into an implementation. So yeah, there's the general idea. Here's a queue: front, rear, size. We add something, we remove stuff, whatever. Edge cases, this is what we were just talking about. What would the linked queue look like if it was empty? What if it had one element in it? That's what we were just talking about. So let's start the implementation. All right, so public class linked queue, generic implements a queue. Remember, very important. And again, don't forget that as soon as you write this in like IntelliJ, IntelliJ is going to be like, but you didn't implement everything in the queue. Yeah, because in the queue interface, yeah, because we're writing it now, right? So if and when you do this and the IntelliJ is yelling at you that you didn't implement all the methods that you said you're going to implement, yeah, it hasn't given you any time to do that yet. So what do we need? Private node, front, private node, rear. Remember, these aren't really nodes, though. They're references to nodes. And then private int size to keep track of the size. The constructor, well, makes sense. If we create a queue, it should be empty. So what should that look like? There we go. Create a queue. Upon creation, its size is 0, and its front and rear should be null. Yeah?
Let's say you want to like test one of the methods before like write everything. Is Joey gonna compile what you wrote or not?
No, it won't. It won't even, like, it'll be like you broke the contract. Saying, like, you said you're a queue, and you haven't implemented everything. So what people will often do, and IntelliJ will even, like, if you hover over and you select, like, more actions, like, sometimes it tries to help solve the problem. If you do that, what it'll do is it'll, like, implement all those methods, but it'll just be like, returns null, returns 0, returns null. It's just returns a bunch of nonsense, but they at least exist. So Java will compile, and you can, like, run some tests. The things you didn't implement are obviously not implemented, but that's a quick and easy solution. If I...
So, like, the implements thing when you're creating a new class, is the entire point of that literally just so that you don't forget to add any of the things you're supposed to?
Not quite. That is one of the things you get from it, is like it forces you to have it. But when you say you implement something and you implement something, that means any code that expects a queue is guaranteed that it has InQ, DQ. So it creates like a contract saying if this thing truly does implement a queue, it might not be implemented correctly. There's no guarantee on like that you implemented a queue correctly, but it does guarantee that all of the methods that are required for a queue to be a queue do exist in the class you're implementing. So if we just looked at the interface, it's just the series of the names. But here, if I start implementing this, I must, before Java will compile, I must implement dequeue, enqueue, first, size is empty. I must. So if it compiles, they must exist. And anything that needs a queue can use a linked queue, or an array queue, or a flimflam queue, or what other implementation you have. As long as it's a queue, Java can guarantee I can call these methods. That's why. So you also do get the added benefit of like, remember, you need to do this, but yeah. Now to the question though, so here's a linked stack. If I go here and I delete everything here, now it's going to be like, you didn't implement any of these things. So I can say, okay, implement methods, and be like, yay, okay, implement these for me. Now, IntelliJ is not that nice, because it doesn't actually do anything. It's just like, okay, it exists now, such that it'll compile, but obviously that pop isn't doing a pop. It's just there, so it makes Java shut up. Yeah.
You said that how we implement a stack, if it's a linked or an array stack, it don't matter. Let's say you have both, and for optimization thing, you need to use one or the other for some certain problem. Is there a way to like choose which one you use when you call them?
Well, it would be upon creation, right? Like, if we go back, like, this is a really good question. If we go back to, like, down here, right? Here's some super important code. I'm using my stack. All this super important stuff, right? But then someone comes along to me and says, no, no, no. You were using an array stack. Don't use an array stack. You want to use a link stack. Here's why you want to use a link stack. And I've got like 1 billion lines of code using this stack. Super important. It keeps the nuclear fuel rod in check on our spaceship, okay? Very important stuff. But someone tells us, like, if you change this out, you're gonna save so much power and we'll be able to get to Mars, right? Great. So I need to go and change it, right? And then you're left going like, but how can I change? All I have to do is notice that the reference variable type here, it's a stack, not a queue, but the same idea. The reference variable type is a stack. As far as the reference variable my stack is it must be referencing a stack. It doesn't care what implementation it is, as long as that implementation is a stack. And it guarantees it's a stack because we implement the interface. If we didn't, if the link stack didn't say public class link stack implement stack, if it didn't say implement stack, Java would say, I can't do that. That would not run. But because we guarantee it's a stack, it's all good. So if I want to change this out, all I have to do is delete that line and change it to array stack or flimflam stack, whatever we want to call it. And then suddenly, like what I like to say, it's not even like, oh, go change 1 line of code. No, change half of 1 line of code. And then you can change out a whole implementation without, like, look how easy that was. That's amazing. Because the what and the how, entirely different. What do I want to do? I want to push, I want to size is empty, all of that stuff. That's what I want to do. How did it do it? I don't care. I don't care. That's the link stack's problem. But when I use the stack through my reference variable, I know what I want to do. I don't care how it does it, as long as it does it. That's the whole magic there. That's what's quite cool about all this. All right. So in queue. Now, have a look at this code. Take a moment, look at it. See if you can make sense of what's going on here. This solution is perhaps a little bit more elegant I guess kinda, we could, but maybe in its elegance, it's actually kind of harder to understand, but just have a moment, look at it. All right, let's end here for now. Any last questions? All right, I'm going to leave you on this cliffhanger. And we'll figure this out tomorrow. Or, do we have class tomorrow?
No.
Friday. Ah, that's a hell of a cliffhanger. I'm sorry, guys. Holy moly. All right, I'll see y'all. So, although I'll see you in lab, right? Yeah, yeah. All right.